Hello, everyone. Welcome back to SAT Math Question of the Day with Professor Emeritus Chaiken, University of Albany, and Joel Chaiken. Today's Wednesday. Yesterday, we had an interesting video where you can watch it where we made a mistake. I haven't actually uploaded it yet, so that day, November 8th, is going to be a little late. Anyway, so here we're back again. If you'll still take us to help you try to approach SAT math questions. So I haven't read this thing. This is big time reading, and this is a calculated question. It looks more like a statistics thing or interpreting graphs. So I guess we all have to be quiet because this is going to take a while to digest. So here we go. We have a graph. I guess we'll just read it ourselves. Um, hmm. Quiet? Oh, not for me. Someone else, like the cat. Okay. The magnitude of the rate of change. At least they're not talking about the average rate of change. Oh, no, they are. They are. They are talking about the average rates at which the temperatures change. But here they don't talk about average rate of change. They're just talking about rate of change. That's right.
Yeah.
So that's good, I guess. Wow. Now this is question 27 of the last section of the SAT. I don't think anyone really wants to have this question. There's so much to digest to see which one is right. So many choices. Oh my God.
Okay. Well, notice
Okay.
that in each of the choices starts the same way.
Okay.
In every 10-minute interval,
Yeah.
and then it's slightly different. In the intervals from 0 to 10 and from 10 to 20,
Right.
and then in the intervals from 40 to 50 and 50 to 60.
Right.
Then choice D is also about the intervals from 0 to 10, 10 to 20, and about 40 to 50 and 50 to 60.
Right.
So they're all common.
Yes.
And it's about the rate of change in an interval.
Right.
Well, that rate of change is proportional to the slope
Absolutely. Right.
of a line that what happens.
Yeah.
Okay.
Just go
When
like.
I press it too long,
Yeah.
the interval, so I'm going to draw a line from here to here
Yeah.
that connects two gray boxes.
Right.
And then I'm going to draw a line. Notice that the gray spot and the black spot are the same at time 0,
Right.
which manifests that both samples start out at the same temperature of 60.
Sure.
And so the corresponding line for the black boxes, for the black dots, for the non-insulated case is that.
Right.
And so so the rate of changes in 0 to 10 interval are proportional to the slopes.
Right.
And so the rate of change of the non-insulated in interval 0 to 10 is bigger than the rate of change of the insulated.
Right. Yeah, the slopes are bigger. Yeah. So
Now, if we go to the other side, I'll connect. No, please don't do that.
Why not?
Take it off.
You got to go from
I'm
0
going
to 10.
all the way to the other side.
Okay.
The line that indicates the rate of change for the non-insulated case between an hour and an hour and 10 minutes later, that slope is practically 0.
Right.
But the corresponding line whose slope is the rate of change. Let me fix that.
What are
Okay,
you
see, it's
doing?
so unstable. What happened? I selected it.
Okay, just start again. Wow. Wait, let me fix it.
Maybe let me try this. Okay, I'll redo it. Redo.
Go ahead.
So see the blue lines. What the blue lines were at the bottom of the top, I forgot.
So let me fix it. Let me fix it. This line here goes here, and this line here goes here. Okay.
Good.
Now
so,
go ahead.
Now I'm going to draw the blue line over here.
Right.
And the red line, make it red.
Yep.
Over here.
Right.
Okay. So that blue line is really horizontal.
Right.
Which, physically, the non-insulated container, after a while, becomes the same temperature as the surroundings, which is 70 degrees. However, the insulated container still is a bit warmer.
Right.
It remains warmer longer, but as it gets close to the room temperature, the rate of change goes down.
Right.
And so the rate of change of the insulated sample over here is bigger.
Right.
The rate of change of the the rate of change of the insulated thing, the slope is smaller. The red is smaller than blue. The rate of change of the non-insulated at the beginning is bigger than the insulated. And the rate of change of the non-insulated at the end is smaller.
All right, so these are out.
And so that rules out A and B, because A and B are both about every.
Right.
Every.
That's good.
Is 6 intervals, but that includes 0 to 10 and 6 to, and so something is untrue.
Right.
About either of them, then it's untrue about all of them. It's not. Right. It's not true that it's true about all of them.
We know. Move
so
on.
We rule out A and B.
I know.
So we just have to choose between C and D.
Right.
And there you don't even have to bother looking at 0 to 10 and 10 to 20. All you have to do is look at 0 to 10 and 60 to 70.
There is no 60 to 70, Seth. It's 50 to 60. It's 40 to 50 and 50 to 60.
Oh, okay. So I should have drawn the blue. I should have drawn the red thing there and the blue thing there.
Right.
But the same phenomenon holds. The red has larger slope between 50 and 60, and the blue has larger slope between 0 to 10. So figure out now now we have to be careful in reading this. Which one describes the situation that we see?
That's right. You got to be really careful.
So you want to talk that out carefully?
What? Yeah.
You try talking that out carefully.
Okay, fine. So Seth's right. We're just going to be concerned with the end. So you can see already that the slope of the blue one, which is the uninsulated one, the colder one is 0, basically flat. And then the slope of the insulated one insulated one is less is obviously less than zero. It's a negative slope. Now,
Yeah,
well,
but they're all negative slopes.
right, but they're also
Except
magnitude.
eventually they become so
I know.
close to zero you
Right.
can't tell.
I know. So the magnitude of this one is greater. The magnitude of
Yeah.
this one's greater, right? It's a negative slope, but the absolute value of it is greater. Okay, so let's see. So I'm going to take some suggestion. Only look at the end. Whereas the interval, the rate of change of the non-insulated one is of greater magnitude.
Okay, I should have noticed that.
Seth, you said I can.
They're talking about magnitude.
Seth,
Yeah.
you said I could do it.
Okay.
Okay, so let me
Yeah.
do it. Okay, yeah. So then this looks really good because the slope, the non-insulated one, has a slope of greater magnitude because it goes like this, and the other one is like this. Magnitude means the absolute value. It means just the number, not whether we don't care if it's positive or negative. Anyway, let's give
the
this
slopiness of the slope.
Okay, come on. And now this one, the rate of change of the insulated. Wait, the rates of change temperatures. Wait.
Yeah.
Oh, where the interval, the rates of change of temperature of the insulated sample are of greater magnitude. Oh, yeah, the insulated sample is of greater magnitude. The insulated, see, it's an English thing. The insulated, this way I had to read both. The insulated samples of greater magnitude, of course. The insulated one, that's this one. It's this one, yeah, because that one's still cooling off, where the uninsulated one has already reached room temperature. So notice I sort of like got it wrong here, but I was humble enough. I had enough humility to realize, oh, I better check this one out too, because this is really tricky stuff, particularly when you're on question 27 and your brain is fried anyway. So I would say it is this one. Now, Seth, do you agree?
Is it? Okay.
Okay,
Let's check it out.
Go ahead.
Now let's talk it very carefully and slowly.
You don't think I
did
it very carefully and slowly? I thought I did.
I am not sure of what you say.
Fine.
So let me check it out really carefully.
Check it.
So what you marked in the blue box.
Actually, this is the answer.
Reads as follows. Okay.
Just to make it clear.
Do I have the floor?
You have the floor.
Okay. In the intervals from 0 to 10, and I'm going to ignore 10 to 20, the rate of, since one interval I'm talking about, the rate of change of the non-insulated, which is gray, is of greater magnitude than the insulated.
No, it's not gray. It's the rate of change. Non-insulated is black.
Oh, okay. Let me read it again. Oh, sorry. So we were flubbing up. Okay, I'll try again more carefully. Okay. The rate of change at the beginning of the non-insulated sample, which is the black dot, is of greater magnitude than the other. Whereas at the end, the rate of change of the insulated, which is gray, is of greater magnitude than blue, and I agree.
Good.
Okay. I agree.
Yeah. Now you were.
But, people who are listening, you have to think these things through all by yourself. After you listen to us explain it, the only way to learn this is to stop the video, stare at the contents of the problem, read it, and make the connection in your mind all by yourself. And that's how you learn. That's how you learn the thinking process. So the approach, approaching SAT problem is a matter of applying a thinking process. And like playing basketball, the only way you could really learn to engage, to do a basketball process or a thinking process, is to do it yourself.
Right. Now you will find, and I think we actually are going to go to Khan. It's probably pretty soon. You'll find practice questions like this on Khan Academy, the Khan Academy practice questions. These questions with a million words. But really, it's an interpretation of graphs. So I think the ACT, I don't know how many people take the ACT. The ACT is very heavy into this. You know what the ACT does? They give you a whole 30-minute thing with one experiment, and they ask you to analyze the whole thing. Here, the SAT is just one question. So that's the difference with the ACT and the SAT. So, yeah, but it's interesting, right? Because you said in your thing that, you should only be concerned about the 50 to 60 thing. But then when you read it, you spent some time on the 10 to 20 where you really didn't have to. Like when you read the whole answer, you didn't really have to read the first part. You said yourself, we're only concerned about the 50 to 60. You don't really even need to read. You didn't even need to read when you were reading it, this section. The first.
Well, anyway. I realized the point of the question was comparing the magnitudes of the two rates of change over the whole experiment and asking whether those magnitudes compare the same way over the whole experiment or whether they compare differently as the experiment proceeds. It turns out that they don't compare the same way throughout the whole experiment. And then they differ. They differ from at the beginning of the experiment, at the end of the experiment, and then the question to discern between answer B between C and D is which way they differ.
Right.
That's a pretty symmetric question.
Yeah, but that was really.
But you have to read it carefully to pick up to connect the the geometry on the graph with the idea of greater magnitude with what's said in words.
Right. Yeah, the key here is the slope. The rate of change is the slope. That is such an important overall concept. The rate of change of a graph is its slope. That is absolutely fundamentally.
Well, there's a technical thing. The thing slopes. Yeah. So in some problems, in some contexts, the rate of change might be positive or negative. In other contexts, the rate of change is, say, always negative.
Right.
And when the rate of change always has the same sign, then it's natural to forget about the sign and compare when the rate of change, when the magnitude, in other words, the absolute value of the rate of change, is bigger or smaller. So of course, so saying changes a lot. Well, that suggests you're talking about the magnitude.
Right.
Yeah.
Okay, I think we're done with this.
Yeah.
Okay.
But also, this problem. This problem is about elementary physics.
Yeah. Seth was, by the way, footnotes. Seth majored in physics, undergraduate.
Yeah.
So Seth always looks at the physics thing. But when I was reading it too, you can understand it. This is intuitive. The thing that's a non-insulated cup, the tea, the coffee cools down faster, cools down sooner. Like in 40 minutes, it's already sort of a little bit above room temperature.
Yeah.
This one here, in 40 minutes, it still feels a little warm. You know that from experience.
So when the container is not insulated, heat, the thing is insulated versus not insulated. For a given difference in temperature, the rate of heat flow is more when the separator is insulated than when it's when the separator is non-insulated.
Right.
The rate of heat flow is greater for non-insulated barriers than insulated barriers. But the rate of heat flow is also proportional to the difference in the temperature.
Yeah, well, now we're getting into
And
stuff.
so when the in the case of the non-insulated container, it cools rapidly.
Right.
And then when it becomes almost as cool as the environment, the heat flow becomes very, very small because the tea and the room are practically the same temperature.
Right. Right.
Whereas
right.
for the insulated one, the temperature doesn't change much at the beginning, but it stays hotter longer.
Right.
So later, the tea is still hot, and since it's hotter than the outside, more significantly, there's still heat flow. There's still significant heat flow, and so you could observe still there's a rate of change.
Right.
So at the end, the rate of change for the insulated thing is higher because the tea in the insulated container is hotter than the outside.
Right.
Whereas at the beginning, the rate of change of the insulated tea temperature is lower because both the insulated and non-insulated samples start out hot, the same temperature, but the change of the insulated is lower because heat cannot flow through the insulated barrier that well.
So you have competing forces. The Zeitboard thing froze a little bit. But this is but you won't, unless, if you major in physics or engineering, okay, you will learn that, just to write it down, the heat flow is really, the amount of heat flow is proportional to the temperature difference.
Temperature difference, yeah.
Temperature difference. Yeah, I from experience.
And it always flows from hot to cold.
Right. So this is an interesting question people could look up if they own a house. Most people taking the SAT don't own a house, but some people live in a house. Is it better during the day to put the thermostat really, really low to save energy, and then when you sleep, or maybe at night, is it better during the day to keep the temperature at a constant? Is it cheaper? Is it more economical to keep the temperature at a constant rate in your house in winter if you live in the north? Or is it better at night or during the day to kill the heat and let the temperature sink down pretty low in the house? You could Google that. Different people. It has to do with the amount of heat that you lose is proportional to the difference between the house temperature and the outdoor temperature. So the colder your house, the less heat you lose. But then you have to reheat your house. So it's an interesting thing. So that's like a practical thing from this. So anyway, okay, I guess that's it, right? Yeah, we did a little physics. Okay, everyone have a good day. I still have to post yesterday's embarrassing video, but hopefully look for that. And tomorrow's Throwback Thursday. Okay, everyone, have a great day.
Bye-bye.
Take care. Bye.
Okay.